Hey guys, welcome back to the next video. In this one, we will be covering what is known as the Wittig reaction. And just like in the past few videos, it mainly concerns carbonyls. So, what is this reaction? So I'll write out the basic idea of it. So we're going to use an aldehyde or a ketone. I'm just going to draw a ketone. And we're going to react it with something called a phosphorus ylide. And it basically looks like this. Here's an example of one. That pH, capital P, lowercase h, means phenyl, which is kind of another word for benzene. So it's a phosphorus double bonded to a carbon, and that phosphorus actually has 3 benzenes on it. What is it going to do? If we number our carbon chains, so let's say this is 1, 2, 3, and this is 4, 5, 6. The Wittig reaction is going to connect the 2 carbon chains together through a double bond. So how do we do it? We go 1, 2, 3. Wherever that double bond of the O was, we redraw it, but without the oxygen. And at the other end of the double bond is that carbon that was double bonded to the phosphorus. So that's 5, which is connected to both 6 and 4. And so we create an alkene using our aldehyde and ketone and our ylide. Now, there are multiple versions of the Wittig reaction. First off, let's figure out how to actually make this ylide. Okay? So how to make the ylide. So you start out with a phosphorus connected to 3 phenols. You can just write it out like this, so you don't have to write out 3 benzenes. And we are going to react with an alkyl halide. Generally, it's an alkyl bromide. And this is a nucleophile that is going to do an SN2 reaction. And so what we're going to do is we're going to use generally alkyl halides that look kind of like this. Notice that this is a primary alkyl halide. Because this is an SN2 reaction, it will not work on a tertiary alkyl halide. So you can use a methyl, primary, or a secondary alkyl halide, and this reaction is an SN2. So the first arrow is the phosphorus attacking that carbon, kicking the Br out, so it replaces it. So what do we get? We get a phosphorus with its 3 phenyl groups connected to a carbon chain that is 1, 2, 3 carbons in length. 1, 2, 3. Always number if you can't figure out how something looks, and the phosphorus gets a plus. Now what we're going to use is butyl lithium, which looks like this. It's a lithium on a 4-carbon compound. So that's, you can write it as BuLi. So this is a base, and it's a strong base. What it does is it's going to go to the carbon that phosphorus just attacked, and it's going to look at the hydrogens on it. So there's 2 hydrogens there. Let's draw them out. And it's going to deprotonate one of them. So that organolithium compound, which is what it is, butyl lithium, is going to take that hydrogen and it's going to deprotonate that compound. So it's going to come over here, take that H, and it's going to add on to that carbon. Our phosphorus has the plus, and that has the minus. And what happens is they usually resonate with each other. This comes over here and adds it into a double bond so that in the end, our ylid looks like this, neutral compound. You may see it written in this fashion, but the more common one is like this. And if you wanted, you could have done the arrows like the lithium grabbing, the organolithium attacks the H, and this going right to there to form the double bond, so we end up right there. Either way is fine. So that's how we make our ylid. Now, the summary of how to do it, so you don't have to write all this stuff out because you may have to do this in a synthesis, is like this. You can start with your alkyl halide. You can write step 1, P for the phosphorus and pH3 for the 3 phenols, 2 BU Li. Make sure to number them. And all that's going to happen is redraw that carbon chain without the Br and just have that carbon with the Br, so number 1 in our case, it's going to be double bonded to a phosphorus, and that phosphorus has 3 of these phenyl groups, like this. And that's how we make our ylid. Now let's do the actual reaction. So there's a few types of Wittig reactions. The first one is sort of the basic one. So I'm just going to call it the basic Wittig. So we're going to start with our ylid. Let's say it's this one. And it's connected to our phosphorus. And so here's our ylid. And we react with carbonyls. In this case, let's use this aldehyde. So with the Wittig, it can be a little bit complicated. So easiest ways to make sure you're getting everything right is to number. So I number this chain. I number this chain, and there's no specific way to number it. The numbering is just so you can keep track of the carbons. Totally up to you. The carbon of the carbonyl that's double bonded to the O is going to connect to the carbon double bonded to the phosphorus. So 4 and 1 have to connect. So when we draw this, I'm going to redraw this, 4, 5, and 6. 4 should be double bonded, and this N carbon is number 1. 1 is connected to 2, and 2 is connected to 3. Now, because we have an alkene, we have to think about cis and trans, or E and Z. We can inform both of them. So let's say I drew it like this. In this case, if you divide the double bond in half, both of these groups are on the same side. And so that's a Z double bond. I could have just as easily done it the other way. So I could have just as easily instead made it so that 1 was here and went this way. In this case, when we cut it in half, it's going to be the two groups are on the opposite side, making that the E isomer. Which one is the correct answer, or is it both? In the case of the basic Wittig reaction, the Z isomer is the major one. That is something to keep in mind. Even though E is considered more stable, Z in this case is actually your major product. Okay, so that's something to keep in mind. So I'm going to write it here, major, and I will try to create a summary at the end, but make sure you understand how each one works. So that's the basic Wittig reaction. Now, let's say we do the same exact thing, same exact reaction, but let's say we add something new, like this. A benzene with a lithium. What's so special about this? This is a benzene with a lithium. It's commonly written out PHLI, or you could even have, again, BULI, like we did over there. Okay? Now, in our case, when it comes to this version of the Wittig reaction, we call this the extra base modification. We're adding in an extra base, which is what PHLI is. So, what does this actually change? Notice that we didn't change anything else about this. We're simply adding in a new type of, a new base, but the ylide, the carbonyl, hasn't changed. This is how we actually get the E isomer. Having that extra base creates the E isomer. So we would go through the exact same process, nothing changes. But instead of the Z product being the major one, the E product will be the major one. So far we have our normal Wittig, which is going to create the Z isomer as the major one. Our extra base modification Wittig is going to create the E isomer as the major one. What else is there? So there's another one called the HWE modification. What is so special about this one? It doesn't have an extra base. The real, what makes this one different is the ylide itself. In the case of the HWE modification, we have to use a different type of ylide. So I'm going to show you how to make that one first. Okay? So actually, before I even show you how to make it, I'll show you why the yllids are different. In our normal Wittig, we had something that looks like this. This is our normal ylide. And remember how we did that whole resonance thing? That was the reason for why there's a double bond there. So the resonance structure looks like this. Now, in the HWE modification, our yllids are a little different. So our yllids are going to look sort of like this. They're going to look a little bit complicated. So I'll write it out and you'll see, and I'll explain why it looks like this. We're going to use something that looks like this weird structure. It looks really complicated. So first, let's dissect this compound up a bit so that it's not as scary. Remember how we had to add that whole phosphorus with the 3 benzenes on it to a previously existing carbon chain. In the case of our normal ylid, that was this part right here. If you divide it between the plus and the minus, anything from the minus onward is the stuff that we added on. It wasn't the original phosphorus compound. Same idea works here. Cut this, and we create that. The stuff on the right is again the previously existing carbon chain. The stuff on the left was the original phosphorus compound. Why are these, so what's sort of different about this? We can see that this is definitely different, right? But the question is, why do we have it like that? Let's say I redid this exact thing, but with our normal phosphorus. This is our normal ylid. Here is the original phosphorus compound you're familiar with. Here's the attached alkyl group. What's different about this compound now? At first glance, it may be nothing, but what's different is right here. That benzene is capable of resonating with that negative. I can shift this. Let me resonate that downward, and this is going to resonate, and then maybe that can resonate there. And so we can maybe get a resonance structure that looks like this. Double bond there, double bond here and here, and the negative is now on that end. What does this mean? What significance does this have? In our previous reaction, when we did the extra base modification or that basic Wittig, our ylid, the compound right here that we had already on it, didn't have anything that was resonating with that negative. The negative can only resonate with that positive phosphorus. Here, that's not the case. Here we have a group that can take that negative away from the phosphorus. So that makes that an electron withdrawing group. Because it's pulling away that negative, it's making the ylid unreactive. It's making our ylid unreactive. So what's the solution? So instead of using this as our original phosphorus, we use this guy. You may see it written like this in the future. That's just an ethyl group with an oxygen, and there are 3 of them attached to the phosphorus. What's the point of this? Well, these oxygens with their lone pairs are electron donating groups. It makes our ylid really reactive instead of having these withdrawing groups on them. So that's our solution. So we learned how to make our ylid for our basic Wittig and our extra base modification that's parts the same. Now we just have to learn how to make it for the HWE modification. So the way we do it for the HWE modification, we start out with our compound like this. Actually, just making one correction, I wrote this as CF3 by accident. There we go. Okay. So we start with this, but we again react with a alkyl halide. Now in this case, we use this this phosphorus compound specifically when you have a resonating group, like an electron withdrawing group. So in this case, I'm probably going to have something that looks like this. Benzene group, or maybe there's another compound that can resonate with that negative we're going to eventually create. Okay? Now, what happens is this is going to react, and you don't need to worry really too much about this mechanism. All you have to know is that the phosphorus will take the spot, take the spot of the Br, it's going to have two of these oxygens with ethyls, and one of them actually becomes a double bonded O. You don't really need to know the mechanism. All right, now, once we have that, we're going to again have to create that negative charge. So we can use our BuLi just like in the original one. It's going to take the H on the carbon the phosphorus is connected to, and it's going to put a negative. And so we're going to get the negative we want. Like that. All right, and that can resonate with this. Puts the double bond there, and this comes up. It keeps those electrons localized next to that phosphorus. And here's our resonance structure. Now, how do we actually do this when we're doing the HWE reaction? So let's say we took this ylide. You may see the full phosphorus compound written out, or you may see it written like this. So be familiar with both, and again, I'll write out a summary. But it's going to have a phosphorus, and it's going to be written like oxygen, parentheses, C2, H5, O2. Oh, sorry. Like that. Same thing. Color this in. And that's this. Two ways of writing the same thing. Once you have that, you can use a regular carbonyl. Doesn't change anything. So let's say we stuck with this one. And again, these are just the same compounds reacting, just written different ways. The principle of how we actually do the reaction is still exactly the same. The carbon with that negative, or if you chose to draw the resonance form, it's the carbon double bonded to the phosphorus, is going to connect to the double bonded O carbon. So we rewrite this. Eight is double bonded to the carbon with the negative, or again, if you drew the resonance structure, it would be the carbon double bonded to the phosphorus, which we numbered as number 1. And in this case, remember, we always have to consider E and Z. In the case of this HWE modification, what we're going to do is we're going to end up with the E isomer. So our chain, our benzene ring, is going to attach to make it so that the chain goes in the opposite direction so that the big groups, the carbon chains are opposite each other. So 1 was connected to 2, and 2 was part of the benzene ring. Three, 4, 5, 6, 7. And that would have been the same exact product for the bottom one. Wouldn't change anything. So in the case of the HWE modification, our E isomer is the major one. All right. Now the very last reaction, before we just go and write out our summary, still plays off of this HWE modification. We're still using a resonance stabilized ylide, which means an ylide that's got some sort of electron withdrawing group. But we're going to add a slight modification that allows us to get the Z isomer. So how would we write it out? In this case, the way you make the ylide is exactly the same, but instead of writing this, we write a slightly different version of it. So this is written out like this. And so I won't write out the full way of making the ylide, but because it's exactly the same as this, the only difference is that the starting phosphorus compound has carbon with 3 fluorines at the end. This probably seems like a lot, but the part of it being a lot is really just making the ylide. That's kind of the complicated part, and maybe the structures look a bit complicated too. But everything else is very, very similar of how to actually do the reaction. Making the ylides vary a bit. So there we have that. And again, the very last difference, and this is the very last part that makes this different, other than the structure, the fact that we have CF3s here, is instead of using like BULI to deprotonate this, we use a slightly different base. It looks really complicated, but it's the only part that's really different, and it can be written out with a few letters instead. But the structure of the base looks like this. And usually there's like a K plus floating around because it is a salt. Looks complicated, but this is just called KHMDS. It does the exact same thing. Deprotonates. And so we can have our negatively charged compound here. Notice the end result is really the same as the regular HW modification, except this is a CF3 here. After that, the reaction works the exact same way. The only difference is our major product isn't going to be the E isomer. It's going to be the Z isomer. We connect it the same way though. I would number it like this. And I would write out the carbonyl compound carbon chain. 8 was double bonded. 8 is going to be now connected to 1, that's got the negative. But in this case, since it's C, it's going to go here so that both of those chains are on the same side of the double bond. And now we get the Z product as the major. So that was the 4 types of Wittig reactions. It definitely was a lot. It's a little bit complicated of how to make the ylid. In the next video, we're going to go through a little bit of a summary so that you guys have a condensed version and don't feel like so it doesn't overwhelm you guys. So I hope this video made sense, and I will see you in the next one.